Hello and welcome to a new video. Today we're talking about limits involving infinity. Specifically, we'll go over the cases of number over zero, number over infinity, and infinity over infinity. Let's start with our first example. Limit of 1 over x as x approaches 0. The first thing to always try when evaluating any limit is to substitute. So I get 1 over 0, and I know that we cannot divide any number by 0, so this is undefined. But it's actually not true to write undefined here, because I didn't say x is taking the value 0. I said x is approaching 0, so x is never 0. So this is wrong. How do I find this limit? Let's take the table of values and see what we can compute. So again, let's take values of x that are close to 0. I'm not interested in 0 itself. So let's approach from the right side. And approach from the left side. And we will evaluate 1 over x. I will fill out the values. So notice that when I'm approaching the value 0 from the right side, the values of 1 over x are increasing. Not just increasing, we are getting bigger and bigger values, 10, 100, 1000, and if I take even smaller values, so think about this as 10 minus 3, 1 over x will be 10 power 3. 10 to the power minus 7 will become 10 to the power 7, and so on. So it's like the values are actually approaching plus infinity. And if I approach the value 0 from the left side, look at the values of 1 over x. Minus 10, minus 100, minus 1000, minus 1 million, minus 1 billion. So they're actually approaching minus infinity. So actually, 1 divided by 0 will not be undefined, because this is not actually 0. These are numbers closer to 0. Instead of writing undefined, we are figuring out that the value is infinity. It can be positive or negative infinity. If I want to be more specific here, we can talk about the right limit. So if I'm approaching 0 from the right side by taking values bigger than 0, the limit will be positive infinity. And if I'm approaching 0 from the left side by taking values less than 0, so it's 0 minus, the limit will be minus infinity. The conclusion here is, when you are replacing in a limit and you end up with any number divided by 0, the answer will be either a positive or negative infinity. So we don't have to do the table every time. How do you know if it's positive or negative infinity? You have to look at the signs of each part of your limit. So let's see how this limit looks on the graph. I have the point 0 here. I can approach from the right side, or I can approach 0 from the left side. So let's deal with each one separately, since we got two different answers for these limits. Let's start with the limit as x tends to 0 plus. If you remember, that was positive infinity. And the limit when x tends to 0 minus, that was negative infinity. Let's start with the first one. So I'm approaching 0 from the right side. So I'm choosing values of x that are greater than 0, and I'm trying to choose the points as close as I can get to 0. If I read the y values of these points, I notice that the points are going upper and upper on the graph. It's like the points are reaching higher and higher, and this means in another way that the values of these points, the values of y of these points, are much bigger, so in a sense they're approaching positive infinity. If I look at x approaching 0 minus, so I'm talking about values of x that are close to 0, but we're approaching it from the left. They are less than 0. If I locate the points on my graph, the closer I'm moving to 0, the smaller the value of y. It seems the points are going towards negative infinity. They're going downwards again and again, and that's why we are ending up with negative infinity. So let's take this other example, and here we are saying x is approaching infinity. You will see a lot of these examples because limits help us study the behavior of a function where it is undefined, like the examples we saw before, and at infinity where we don't have a specific value. So if I replace, I will end up with 1 over positive infinity. And later on we will be able to fill this directly. But for now, let's explain where this answer is going to come from. So x is approaching infinity. We don't have values for infinity, we're just thinking of large values. So I'm going to take some examples just to highlight what infinity means. So if I'm taking 1,000, 10,000, and even a million. Keep in mind, I can write each of these as powers of 10. I want to find 1 over x. So this is like 1 over 10 power 3, which is the same as 10 to the power of negative 3. If I want to write this as a decimal, this is what I'm ending up with. Same thing here. Same thing here. So notice the values of 1 over x. They're so close to 0. They're almost 0. So the answer is actually 0. And we can take this as a rule. Anytime you are substituting to find a limit, if you're ending up with a number over infinity, whether it's positive or negative, this would be 0. And I will remind you of the other rule. Number over 0 is infinity. If we look at our next example and try substituting, you'll just end up with infinity over infinity, which is not even a number. So we have to think of a different approach. The way we will approach these problems is by taking out the highest power of x. What do I mean? So the highest power of x in the numerator is x squared. I only have that. I'm going to factor the x squared out. So x squared times something to give me 2. 2x squared, so I need a 2. X squared times something to give me negative 5. So I have this extra x squared. This way, when I actually multiply out, the x squared will cancel. I will do the same thing for the denominator. Take x squared out. I'm left with 1 here. X squared times something to give me 3x. So I need the 3. And I need to get rid of one of the x's to go from x squared to x. So I'm going to divide by x. Why am I doing this? I'm interested in these. If I actually replace here, this will be a number over infinity, or infinity squared, which is even bigger than infinity. It's another infinity. And we said a number divided by infinity, whether positive or negative, is 0. So this is 0. 3 over x, 3 over infinity, number of infinity. This is also 0. X squared and x squared, they are exactly the same. I will cancel. So what am I left with here? 2 and 1. So the answer is so again, we're working with limits at infinity. I will use the same approach. Factor the highest power of x in each of the numerator and the denominator. So for the numerator, the highest power of x is just x power 1. I will factor this 1 out. So I will have x times 1. And I need to get rid of the x to get back the 3. So this is 3 over x. Same thing for the denominator. The highest power of x is x squared. So I'm left with 1. X squared to become x, I need to get rid of 1x. X squared to become 1, I need to get rid of the whole x squared. You will always end up with things becoming 0. X is infinity. 3 over infinity, number over infinity, this is 0. Number over infinity, again 0. Number over infinity, again 0. And then I have x and x squared, so I can cancel 1x out, and I'm left with x. Let's try to replace. In the numerator, I end up with 1 times 1, which is just 1. And in the denominator, I'm left with 1x, x being infinity. Number over infinity is 0. Another way to see this is to remember that whenever we're dealing with infinity, we are just looking at the behavior of the highest powers. So this limit translates to just us looking at x here. Because when x is a very large number, like 1 billion, adding 3 to it will not affect it. It's still 1 billion. So I will neglect the 3 altogether. Same idea. If x is 1 billion, x squared will be much bigger than the 5x and the 1. So they will barely affect it. So when I'm looking at this function, I'm just looking at the one with the highest effect, which is the x squared. So this basically becomes cancelling out x, which is what we did here. Last example. Limit of x cubed plus 1 over 2x minus 5 as x tends to negative infinity. Negative infinity or positive infinity, it's the same approach. So factor out or take out the highest power of x in both the numerator and the denominator. So I will take out the x cubed. I'm left with 1 plus 1 over x cubed. In the denominator, the highest power is just x. So I'm left with 2 minus 5 over x. Since x is tending to or approaching negative infinity, I know that these will be a number over infinity, a number over infinity. So both of these are 0. I just forgot to highlight that infinity to a power of 2 or a power of 3 or a power of 5, any positive power is still infinity. You're just making it even bigger. So that's why this is still a number of infinity. So what am I left with here? X cubed and x, we can cancel an x out, so I'm left with x squared. So from all of this, I'm left with limit of x squared over 2. 1x is infinity. And this is also infinity. Keep in mind, infinity is not affected by numbers. Whether you multiply it by 2, divide it by 2, it will not have an effect on such a large value. So the limit is again infinity. So let's summarize the 3 cases that we had here. trying to find the limit of a rational function, meaning here f of x is a polynomial and g of x is a polynomial, when x is approaching infinity, whether positive or negative. We have three cases. Case 1, degree of f of x is less than degree of g of x. In this case, you will always have a variable left in the denominator, so you'll end up with a number over infinity, so the limit will be 0. The second case, degree of f of x is equal to degree of g of x. In this case, the x's will cancel out, so the answer will simply be a over b. What do I mean by a over b? A is the leading coefficient of f of x, and b is the leading coefficient of g of x. Let me just remind you what a leading coefficient is. So if I'm looking at this, so here the two functions f of x and g of x have the same degree, which is x squared, so the degree is 2. The leading coefficient is the coefficient of the variable with the highest power. So the highest power in the numerator is x squared, so this is the leading coefficient. For the denominator, it's x squared as well, so the leading coefficient is -3. So for this example, the limit will simply be 2 over -3 or -2 over 3. Third case is when degree of f of x is bigger than degree of g of x. So in this case, as the example we've seen, even when we cancel out x's, we will still have x, or the variable, in the numerator. So you'll still have an infinity left, and in this case, limit will be infinity. Thank you for staying with me till the end of this video. Don't forget to like, subscribe, and share.